Greetings, fellow humanoid dwellers. In this electronics tutorial, we're going to go over resistors again, but we're also going to look at voltage and current and show you that voltage and current are two separate things, and the way you measure them is different also. We're going to use two different values of resistors. If you remember from the last tutorial, we can tell the value of it by using our trick saying, and we can use this one by big bird, which is brown, 1, and big, which is black, so that's 10, and big bird runs, which is red, so that's 2. So 1000 is a 1K or 1000 ohm resistor. We're also going to be using these resistors over here, which the only thing we change is the other band, which is orange, and it's big bird runs on, so that's 3 zeros, so this is 10,000 or 10K. I have 3 meters on, all measuring voltage. I have a circuit that starts with this power supply, which we can adjust the voltage on. It feeds, the positive side feeds into here, runs across here, runs down through this resistor, keeps going, uses this wire to go across, goes down, comes across, and goes back up. I have a voltage meter to measure across this resistor. I have another voltage meter to read across this wire, and a third voltage meter to read across this final resistor. When I start the simulation, you'll see everything will fire up. I set the multimeter to run 30 volts. The current is 15 milliamps. And the voltage across this resistor is 15 volts. The voltage across this wire is 0 volts. And the voltage across this resistor is 15 volts. Whatever the total voltage is, it gets divided up amongst all the devices in your circuit, including the wire. But the wire has such small resistance, it acts like a short, and it doesn't have any voltage across it. And since these resistors are equal, the voltage is divided across them. Don't worry about calculating anything in this example. I just want to show you a couple things. We'll get into how to calculate things in future tutorials. Just for right now, I just want to give you an overview of how voltage and current work. So if I stop the simulation, I take this resistor out, I put this resistor in. If I start the simulation again, take a minute here, pause the video if you need, and try and think in your head what's going to happen. This is 10 times more than this resistor. The voltage across this resistor is 10 times greater than the voltage across this resistor, which makes sense because this resistor is 10 times a greater value than this resistor. As you can see, this green wire though is still reading 0 volts. The main reason that I included this in here was to show you that you could also measure current. The current is displayed. We're currently drawing 2.73 milliamps. As you can see that the voltage is different across each resistor, the current is the same throughout this whole circuit. When measuring current, the meter needs to be in series with the circuit. Right now, this meter is in parallel, and it's in parallel with that wire. The wire shorts out the meter, which then stops the meter from being able to read the current. I will show you that. We'll stop the simulation. We'll change this to amperage, which is the same as current, and we'll restart the simulation. As you can see, there's 0 amps flowing through this meter. The reason that is because in a parallel circuit, the current will choose the path of least resistance. So this wire has 2.73 milliamps running through it because it has less resistance than this meter. So if I want to measure the current, I have to remove this wire. So we're going to stop the simulation. I'm going to move this over to here. So I've broken the circuit now. The path is up through here, around, down, and through here. If I start the simulation again, you'll see that we get 2.73 milliamps, which is the same as here. So even though this resistor has more voltage over it, because it's divided up, 27.3 and 2.73 add together to be 30 volts. The interesting thing is if I change this meter back to voltage, since it's going to read across this instead of passing through this, this resistance is enormous since there's nothing there. So all of the voltage will drop across this opening and you'll have 0 volts here and 0 volts here. Stop the simulation, click on that, change it back to voltage. We'll start the simulation. This did get 3 millivolts, but I believe that's just because this is a simulator and maybe it is reading this at some level that is huge, but 3 millivolts is 0.003 volts. As you can see, this still reads 30 volts. And there's 0 amps. There's no current running through this because this is essentially an open circuit. It's like turning off your light bulb. I'm going to stop the simulation. I'm going to change this back to amperage. Move this over to here. Move this over to here. I'm going to take this one and I'm going to change it to amperage. Now, when I start the simulation, the path is going to go through the meter and around this resistor. And we'll be measuring the current here, and the current here, and the voltage down here. If you need to, pause the video again and think about what you think will happen. Since this meter is reading as essentially 0 resistance, all the voltage is bypassing this resistor, going through this again. Well, actually, since I put this back in, it's bypassing this meter and going straight through here, and all the voltage is being put over this resistor. I'm going to go ahead and stop the simulation and move this over, and this should switch to 30 milliamps. 30 milliamps, 30 milliamps, 30 volts. The main reason for this tutorial is to show you the difference between resistance, current, and voltage. When you measure current, it needs to be in series with whatever you're measuring. When you measure voltage, it needs to be in parallel to whatever it is you're measuring. And also to let you know that voltage and current are two separate things. There's some very simple math that helps you calculate what the voltage should be. And we'll go over that in one of the upcoming tutorials. Thanks for watching.